Okay, lecture 6B, the first of thermodynamics, and we will be talking about the specific heat in this lecture. Continuation of the previous lecture, lecture number 6A. Uh, Specific heat and relation between the temperature and the heat changes. Topic is in one violin, Bonac and Sondek, topic 6.5.6. That would be in a previous version, but in your own book that would be a little bit different. Uh, till now, what we were doing in our lecture was actually finding a relationship of work done always. In our previous lecture, which was the first law of thermodynamics, we did define the relationship of the heat transfer, which was Q, delta Q would be equal to delta U plus, sorry for that thing, delta U plus delta W. So this was the a little bit equation for the heat transfer, but we did not define itself the equation of the heat transfer. What it actually heat transfer, if you remember the first few lectures, we did define the heat, which was the a function of the temperature difference. So if we are talking about the heat transfer, we would be talking about the change in the temperature. So what would be the change in the heat? That change in the heat would be proportional to the change in the temperature. So that mean like delta Q would be equal to any constant, and that would be equal to delta T. So now that means like this is actually a simple heat transfer equation, a simple heat transfer equation. Now what actually this C, and now this is definitely a constant, what we call it proportionality constant, and that's depend on a substance. So you can imagine like it cannot be the heat transfer in an iron, or the change in the temperature in an iron would not be equal to the change in the temperature in a wood or something. So that means like a heat transfer, if you are supplying the same heat transfer to an iron, or if you are supplying the same heat transfer to a wood, actually that would definitely not equal. So that means like the C is depending on the substance itself. Now the thing is like itself, you can imagine like now the question would arise, what actually the C is, whether it's a path dependent property or whether it's a state dependent property. If you can imagine like Q, it's a path dependent as it depends on the process itself. If you define T, actually it's a state property and it depends on the state only. So what about the C itself? You might have heard two different constant of proportionalities. That is actually a specific heat. If I can simply define now, we would define it as specific heat constants actually. One is actually Cp and one is actually Cv. You normally would call it as a specific heat at constant volume and specific heat at constant pressure. So that means like if we are saying like specific heat at constant pressure, so this constant pressure itself is a path. So that means like specific heat is a path function. If you are saying like specific heat at constant volume, so that constant volume itself is actually a path, and you can imagine like Cv would be a path function. But can we just move around and move on? So we can actually imagine like whether it is a path function or a state function. So let's have another look. And let me define as you can imagine in a previous few notes, you internal energy and specific. Let's move on to specific it at a constant volume. Internal energy as a function of TV, external energy as a function of PV, internal energy as a function of as a PT. Let me, for my own easiness and for my own derivation, let me take the internal energy as a function of temperature and volume. And let's differentiate du in a chain rule and rewrite the equation like this. So that like change in internal energy du, that would be du by dt into dt and du by dv into dv as a function of temperature and as a function of volume. So using the chain rule, I can actually expand the equation something like this. I've got another equation, and that is actually of the internal energy. I've got another equation of the internal energy, which is equal to internal energy is equal to Q minus W. Or if you in our previous we say like first law of thermodynamics for the quasi-equilibrium process, Q minus PdV. As we did that, we are talking about the constant volume process. So if you are talking about the constant volume process, so this term would be equal to 0, and also this term would be equal to 0. So that means like change in internal energy would be equal to dq at a constant volume process, and change in internal energy would be equal to this relationship at a constant volume process. So in other words, dq, which is actually this thing, would be equal to this bit. So that means like dq is actually equal to this one. dq by dt is equal to du by dt now. So as obviously our relationship what as a at a constant volume. So that means we will be talking about the constant volume. So going from dq by dt, you can imagine dq by dt somewhere here. So that means like it's a constant. So that means Cv would be equal to change in internal energy by a function of T at a constant volume process. Now let's look again to this equation. If you can look at this one, internal energy it itself is a state function. Temperature itself is a state function. So any state function differentiate with respect to another state function would be again a state function. So that means like from this equation, we can say like the Cv is a state function rather than the path function. But let's move on to another one. Specific heat at a constant pressure process. Using the H enthalpy and enthalpy at a function of temperature and using the similar steps, you can define Cp is equal to dH by dt at a constant pressure process. Again, H is a state function. Again, T is a state function. So again, we will say like a state function, partial derivative of a state function with respect to another state function. So that means like Cp is again a state function. So in derivation of the Cv, we consider only constant volume process. So hence specific heat at a constant volume. So it is more useful, however, to think Cv in term of definition at a certain partial derivative, which mean like a derivative with respect to another function or a function, a state function with respect to another state function. And similarly with the Cp as well, we did derive a one state function with respect to another state function. So in fact, these derivatives above were defined at any point in any quasi-static process. It was rather than actually at a constant volume process, it was not at a constant pressure process or any other process. That mean like in a derivation we did say like we were using the constant volume and constant pressure, but itself this derivation, when we got the derivation, it was not a function of constant volume and constant pressure. So in other words, Cv and Cp are thermodynamic properties which depend on only states. So that in other words, these are called as unfortunate misnomers. What we call it as misnomers, misnomers are like these specific heat are Cp is actually given a name which is not a correct name, or Cv is actually given a name which is not a correct name. These are misnomers. It is does not depend on Cv, does not depend on volume. Cp does not depend on pressure, but only and only when we were deriving them, we use constant volume and constant pressure. Themselves, it does not depend on volume and pressure. So what actually I mean to say, like, if you can actually go down there, change in internal energy now from the above is equal to Cv delta T. Change in enthalpy would be equal to Cp delta T. So now you have got this equation of change in internal energy, change in enthalpy. You can use these equations in any of the process. It is not restricted to constant pressure and constant volume. It is not restricted to any path, but it is actually valid for any other process as well. For a small temperature changes around like 200 Kelvin, it is all often assumed like Cv and Cp are constant. If you've got not so much temperature changes, I mean 200 Kelvin, under 200 Kelvin, you can imagine like Cp and Cv are constant. But yes, like later in our power plant one and power plant two, we'll be studying. So Cp and Cv are not taken as constant as the temperature differences going further. The Cp and Cv are changing. So these are definitely not constants as well. One important relationship we can find out using them is actually relationship using ideal gas equation. H is equal to U plus PV from the previous uh, equation. PV is equal to RT. Uh, is equal to RT for the ideal gas equation. You can just put the RT in here. So H is equal to U plus RT. Differentiating and substituting, we have the H is equal to DU plus RDT and T RD. So if T is constant, so obviously that part would be gone. DH is equal to DU plus RDT. So DH is equal to, from above there, DH is equal to CP dt, du is equal to CV dt, and RT over here again, taking DH is equal to CP delta T, du is equal to CV delta T, taking T common, so that means like it's gone, CV minus CP, CP minus CV would be equal to R. Then there you might have seen another equation which mean like gamma is equal to Cp by Cv. In general, for substance other than ideal gas, obviously these are equations which can depend on many other things, does not only depend on the pressure and temperature. So the above relationship they does not apply other than the ideal gas. So ideal gas is definitely a special case. Many other equation that will be actually having different properties, having complex substance. So yes, for a simple one, you can use these equation, but for now, for a complex one, we will be actually relating them. We will be having different equation then. Let's move to an example. Example 5.6 that might be in your book. A cylinder fitted with a piston has a volume of 0.1 cubic meter and contain 0.5 kg of steam at 0.4 megapascal. Heat is transferred to the steam until the temperature is 300 degrees centigrade, while the pressure remains constant. Determine the heat transfer and the work done in the process. So the work done would be the work done of the constant pressure process going from state 1 to state 2. So if you can imagine, the work done equation would be equal to T V2 minus V1. And if we are talking about the mass and the total volume, so obviously there is a mass involved as well. So just check it. You can easily understand that one. Um, for the heat transfer, so obviously heat transfer would be equal to change in internal energy plus work done. And obviously in a last lecture 6a, we did say like the heat transfer in a constant pressure process equal to change in enthalpy. So that means like H2 minus H1. We did define that one equation, so we will be using this equation, which is actually quite easy. Um, Now, from this equation, we can have a volume which is actually V1. So volume V1 is equal to 0.1 divided by 0.5, that is equal to 0.2 somewhere. And a steam at and a pressure which is actually 0.4. So first thing first, what you have to do is actually go to the steam table at 0.4. Just check the volume at saturated steam table at 0.4. Just check the volume. If it is greater than Vf or less than Vg, so what you can say, like if it is in between Vf and Vg, that means like we are inside the vapor dome. So our volume, which actually I have checked in there, so it was inside the vapor dome. So the state one is inside the vapor dome. Now going back to the thing, the same thing. Let me have another state two as well, which is 0.4. at 0.4, just check the temperature, saturation temperature. If the given temperature is greater than the saturation temperature, so we are in the superheated condition. So yes, our state 2 was in a superheated condition and our state 1 was inside the vapor dome. And you can imagine, like inside the vapor dome, we are moving in a constant pressure process. But yes, outside the vapor dome, the pressure would remain constant, but the temperature would be rising. So the graph would be moving something like this. So that means like work done would be equal to P V2 minus V1. So now let's say have a V1 which is actually over here, somewhere here, and we have got a V2 which is actually from steam table, superheated steam table. We can find V2 which is at 0.4 at 300 degrees centigrade. We have found the V2s over here. So that means like W would be equal to mass multiply by, so that if we are multiplying with the mass, that means like we will not having a specific volume, but we will be having a specific water, but we will be having a total water. So that means like V2 from superheated minus V1, which was actually from there as well, from here as well, would be equal to the work done. Now for the enthalpy itself, finding the enthalpy, H2 can be simplified by using the superheated steam table. So you just go to the superheated steam table. Let me clear it out so you do not have got any confusion in here. So superheated steam table, we have got 0.4 megapascal. So if you can check in 0.4 megapascal, we have got volume here, enthalpy here, and entropy here. And at 300, so volume at 300 somewhere here. So sorry, somewhere, yeah. So volume V2 is equal to 0.6549 and enthalpy is equal to 3.6701, 3.67.1 actually. So that means like the volume was 6.48 something and enthalpy H2 is equal to 6067.8. Now, what about the H1 itself? H1 is equal to, as it was inside the vapor tube, H1 is equal to H1 is equal to HF plus X HFG. So in other words, if you remember, V1 is equal to VF plus X VFG. So at 0.4, at 0.4 in our saturated table, you would be finding HF, we will be finding HFG as well, but obviously we need X over here to find the value of H1. While in other equation of the volume, V1, we have got V1 already, which is 0.2. We have already got VF, which is at 0.4 megapascal. We have already got VFG, which is actually 0.4614. So we find X from here, from this equation. Putting X in this equation, you can find the enthalpy at state 1 now. So now you have got both the enthalpy, enthalpy H1 and enthalpy H2. So you can simply put them enthalpy back in there and you can find the change in internal energy, sorry, change in heat would be equal to change in enthalpy somewhere here. This is the second method, like if you are not looking for the enthalpy, but if you are looking for the change in internal energy and work done, so the equation would be equal to change in internal energy plus work done, and the internal energy you can find from the tables if it is not there. So just use the book table, which is actually internal energy there. And then obviously work done, which actually we have already found out somewhere, yes, over here somewhere, and put them and here. So you can imagine like work done from this equation and sorry, heat transfer from this equation and heat transfer from this equation, they are both the same. I hope you understand that one. If you have got any problem, just post it in a classroom and I would be able to answer. Thank you very much. Have a nice day.